Good. So we have an example of a saturated fatty acid in line notation. So let's draw an unsaturated fatty acid. So again, we start from a COOH head group. This is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. And we put, in this case, a double bond at the 9 carbon, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so this has a general name of oleic acid. Okay, and the carbon number, or excuse me, the lipid number for this is, again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the first number is 18. That's the number of carbons within the chain, colon. And then we have a double bond at the 9 carbon. So we say 1 for the number of unsaturations, comma, del superscript 9. And so that indicates that the fatty acid for this lipid, or the lipid number for this fatty acid, has 18 carbons, 1 unsaturation that starts at the 9 carbon, del 9. Okay? And so this is a monounsaturated fat. Okay? And then we can also draw a polyunsaturated fat. COH, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, double bond, 10, 11, 12, double bond, 13, 12, 13, 14, 15, double bond, 16, 17, 18. Okay, and this one is called linoleic acid. And again, we have 18 carbons, colon, and now we have 3 double bonds, so 1, 2, 3. 3 unsaturations, which are at the carbons 9, 12, and 15. So this is del 9. And I'm going to come down here because I'm running out of space. Usually you just write that all in a line with commas in between. Okay? So the lipid number is 18,3, delta 9, delta 12, delta 15. And so that gives us the lipid number for this poly unsaturated fat. Okay? So now we have the nomenclature, we have the ability to draw these. So what's important about this? So let's first talk real quick about typically unsaturation. So when there are double bonds in fatty acids, these tend to be cis. Okay? So notice how in the oleic acid, both of the carbon groups, the higher priority groups around the double bond, are cis with respect to each other instead of trans. Like this, which, just to remind, this is a cis. And this would be trans. Okay. So for the most part, fatty acids that are produced in biology are going to have this cis conformation. Trans fatty acids, such as when you think about trans fats, which you may hear a lot in terms of nutrition, are usually created by some sort of chemical process. But biologically native tend towards the cis conformation. So that's one thing you typically see for unsaturations in fatty acids. Another one is that the unsaturations tend to be 3 carbons apart. So notice for linoleic acid, the unsaturations are at delta 9, delta 12, and delta 15. So these double bonds tend to occur 3 carbons apart. Now that's not a hard rule, but this is, again, the trend that you tend to see. The other thing you tend to see for fatty acids is, for instance, just for reference, the palmitic acid lipid number is 16,0. Fatty acids in general tend to be have even number of carbons, and that's because of the way they're biosynthesized, which is outside of the scope of this course, but is very important in biochemistry too. And so these are important. The structure of these are important because, for instance, saturated fatty acids, these are able to pack closer together. So if we think of a fatty acid like this, these are able to pack very close to each other, and that in that way they tend to, for instance, form solids. You can think of, for instance, butter, which is full of saturated fatty acids, and these are able to pack very close to each other and you get a solid form. Whereas if there's a double bond, these tend to kink. So they may go like this, but then they go here, because the double bond doesn't allow them free rotation and in order to have this sort of closest packing. So they do this, and in the presence of, for instance, other saturated fats, this spreads the lipids out, and this causes there to be higher fluidity within the membrane. And this is really important for the structure of the membrane, as we'll discuss later.